In this video, we'll finally see how we can train a conditional random field. And so we'll first discuss the loss function that we'll use to train and learn our conditional random field. So in the previous videos, we've defined what we meant by a linear chain conditional random field. So that's the specific conditional random field we'll consider. So P of y given x, where y is a sequence of label and x is a sequence of inputs, is going to be the exponential of a sum of unary potential or log factors and pairwise log factors, divided by a normalization constant that we have to compute with some dynamic programming using the forward-backward algorithm. And thus far, in the previous videos, I've always assumed that our conditional random field was already trained. And I've talked about how we can perform inference, compute the partition function, perform classification, and so on. So now we'll finally look at how we can train a conditional random field on some available data. So again, we'll use empirical risk minimization as our guiding principle for deriving a learning algorithm. That is, we are going to choose a loss function and to train a conditional random field on a training set, that is a set of pairs of input sequences and target sequences or label sequences. We'll minimize the average of the sum of the loss function, where we compare to what extent our model fits well with the target sequence information we have. So we'll optimize this average loss plus the a weighted regularizer to control to what extent we want our model to fit well the data and to be able to control for overfitting. So again, we're casting learning as optimization like we've done in the regular neural network. And though ideally we'd like to optimize the classification error, so in this case, perhaps we'd like to optimize the sum of per label classification error. This error, again, is non-smooth, so we have to use what we usually call a surrogate loss, or an alternative loss that sort of looks like what we want to optimize, but that is better behaved, and specifically in this case is going to be differentiable, so we can perform gradient descent training. And again, we'll use stochastic gradient descent. That is, the way we're training is going to proceed is that we'll first initialize the parameters of our model. And for a certain number of iterations, we'll cycle through our pairs of input sequences and target sequences. We'll compute the update direction, which is going to be minus the gradient of the loss for my current pair of input and target sequences, minus also the gradient of the regularizer, and then I'll take a small step, so alpha times the update direction to change my vector of parameters, my set of parameters. And so again, I have to specify a loss function. I specify a procedure for computing the gradient with respect to the loss function. I also have to specify the regularizer and its gradient as well as the initialization method. So these two parts are not really going to change, so we're not really going to discuss them. We'll focus on choosing a loss function and also specifying how we compute the parameter gradient. And in this particular video, we'll look at the loss function we'll optimize. So again, because a conditional random field estimates the conditional probability of the target given the input, what is a natural thing to do is to maximize the probability assigned to the true target sequence given some input sequence as extracted from our training set. And as we've seen in the case of a regular neural network, instead of maximizing probabilities, we can minimize the negative log of the probability, which is more better behaved and yields simpler math. And so to frame it as a minimization problem, we minimize the negative log likelihood. So our loss function will be minus the log of the probability of the true target. So normally this would be the true target given the input sequence. So this is really the same that we've done in a regular neural network where we have an input vector and we're trying to classify it into a set of C classes. The only difference is that now this is a sequence and this is also a sequence. One sort of subtle difference also is that while in non-sequential classification, if we have 10 classes, we might actually explicitly compute the full conditional distribution P of y given x by iterating over all classes and so obtaining the full vector of probability. Now, with a sequence, we can't do this because the number of sequences is exponential. So really, when we're computing this, we'll use forward backward to get our alpha or our beta table and to compute the partition function. And we'll use then explicitly the partition function into the expression for p of y given x, and then we'll take minus the log of that. So we won't actually compute, we don't have the full distribution over all sequences. That's just because that's too big of an object. It's something that's, there's an exponential of those sequences, so that would be an exponential number of probabilities. So that's the loss function we'll use for training a conditional random field.